Hello, everybody, and welcome to Coffee with Caleffi. I'm Kevin Freet, and it's my pleasure to host today's biggest ever Coffee with Caleffi webinar. Thank you all, our dedicated attendees, any new listeners, and if you're a member of ASPE, we are delighted that you're joining us today. Let's get started with a few housekeeping slides. So if you have any problems with the audio or you lose any technical issues, just log off and log back on. That usually fixes it. Second item, you will receive a copy of today's presentation, yes, if you select that in the post-webinar survey. And all of our Coffee with Caleffi videos are recorded and up on YouTube, so you can view those anytime. Just search for Coffee with Caleffi on YouTube. You will get a certificate of attendance, and if in your region you can get some continuing education credit for that, you can use that. And just to make sure to provide all your information, and we hope that that's useful to you. Hydronics. If you're not familiar with our Hydronics Technical Journal, I highly recommend it as a reference for designers, engineers, technicians, and anyone else in the industry, really. We produce it twice a year. It covers a wide variety of topics in heating and plumbing, and it's really popular for training and education in general. This issue number 34 is our latest edition. It's available online now. And our more recent issues are interactive. On the next slide, you can see it's shown on a tablet. What that means, interactive, is it's searchable. It has hyperlinks and you can play videos. It's a whole new way to access the hydronics journals. Save the date. So our next presenter is a crowd favorite. John Siegenthaler will be up next month, and we hope to see you there for that Coffee with Caleffi. Okay, our guest today is Christoph Lohr. This is the second time he's been a guest host for us, and today he'll be discussing engineering methods that can help designers right-size their domestic hot water systems. Christoph is IAPMO's Vice President of Technical Services and Research. He has over a decade of experience in designing plumbing systems, and he's regarded as an expert in his field. He specializes in the realm of balancing waterborne pathogen prevention and water sustainability. He is a distinguished graduate of VMI, the Virginia Military Institute, with a Bachelor's of Science in Mechanical Engineering. Welcome, Christoph.
Excellent. It's great to be back, Kevin. Thank you so much for having me.
All right.
And I guess I'll go ahead and get started here. So first off, just want to say thanks to all of you that showed up here today. I'm excited to be with you again. Thank you to Caleffi for having me on a second time here in a few months. And I think a lot of the questions from last time is what we're going to be touching on here today, which is really focusing on how to size hot water recirculation systems, especially based on the latest and greatest documents that are out there. So some of this, looking at some of the names, I think some of you I've seen in my classes before, so this will be a great opportunity to solidify some of the topics I've talked about in the past. And for those of you that haven't been involved in this, I'm definitely excited to present something that is really critical in our industry. Worth noting, as an employee of IAPMO, we will not, or I will not be endorsing any specific products, and I cannot endorse any specific products. However, I will have images throughout my presentation of products that comply with standards or classifications or other things. So just want to make sure to make that delineation. IAPMO, we value all of our collaborators and partners that we work with. So really the abstract of what we're going to be covering today is really this focus on hot water sizing and a concept that hopefully many of you know, or many of you maybe know, or a topic that may be new for many of you, which is the Hardy-Cross methodology, which is really something I learned about a number of years ago, actually in my college coursework at VMI. It was a required course. So I'm hoping to really focus a lot on the theory, because really to develop expertise in a system, you need to know theory and practice. And it's that combination of theory and practice that really leads to the best results. And so we're going to be spending some time on both, but definitely heavy on the theory side because it does impact the practical application of hot water recirculation system sizing. Before I dive into the curriculum, though, I do want to share a quick story, and that is when I was working on a healthcare project, was coming in after the project had been constructed. We were looking and finding Legionella positivity at a sink within this healthcare facility, which had multiple parallel branches for its hot water recirculation system. And as I was going through and trying to do evaluation, it was a little bit mind-boggling. There was a really good engineer on the program, somebody that had worked in the healthcare space for many years, so had a reputation as being competent. The contractor was the same thing. The owner, actually, the year before, had won an award for having the best water management program in the country. And all the systems put in place, came from reputable manufacturers, and so everything seemed up for success. And it was really curious why this one sink continually saw Legionella positivity. As we were trying to diagnose it, one of the questions that came up was what was the test and balance report? Was this system balanced? And when we went back and looked, sure enough, this one system had a balancing valve on it that was not balanced properly. And in essence, what it did is it created a gigantic operational dead leg in this one branch that led to waterborne pathogen, specifically Legionella growth, over and over and over again, no matter how much flushing occurred. And so it's worth noting that the hot water recirculation systems, the return side especially, it has a big impact. And we have to think about it in terms of systems. Now, the question we should ask at this point is, why do we have hot water return systems? And the reason for this is we are trying to bring that hot water source as close to the fixture that is being used by. Most codes have some kind of range, anywhere between 10 feet to, or even less than that for public lavatories, all the way to 50 to 100 feet, some of the older codes, or a time of delivery. And the reason for this is the longer you have to keep a fixture open and deliver hot water, that's water that we're wasting. So by recirculating is the term I'm going to use for the circulation that's coming from the hot water source to the building, and that follows ASPE's latest Legionella design guide, which I would recommend getting a copy of if you haven't already. We defined recirculation as that process of bringing hot water from the hot water source to the plumbing fixtures and then back again. Circulation systems we defined as if you have a separate storage and boiler. So just to kind of clarify some terminology, but we have these hot water return systems to bring that hot water source as close as possible to the fixture it uses. And there's any number of requirements from there. So for this class, as I mentioned, we're going to talk a lot about theory. And this came straight from my time at VMI. I had a course that was entitled Energy Conversion Design, my senior year, and it was a required coursework. Now, it seems as if ABET accreditation got rid of this as a required coursework, which during my time mentoring and training and performing quality control with young engineers, I kept asking them why they were getting so confused on hot water recirculation systems and how to design the hot water return side. And I came to find out they didn't have this class as part of the required coursework. So in essence, we're going back to school. The good news is we have a lot of, well, the good news is it's not this many equations. The bad news is there is a few equations that we're going to have to go over. So we'll kind of get back into the mindset of our college coursework. Now, the last time I was on college with Coffee with Caleffi, I brought up this topic of parallel piping systems and fluid dynamics. And I want to cover it again because it is a topic that this is one that we seem to struggle with as an industry, especially the younger designers, and it's worth solidifying this before we move on. I would recommend also viewing that YouTube video as it covers a lot of the topics in terms of setting up, but I want to do a quick rehash of this for our session here today. So if we have two pumps in parallel, each pump is the same pump and only one pump is on, and we turn the second pump on. So two pumps in parallel, the second pump turning on, same pumps, the flow will double and the head increase across the system will stay the same. If we switch that configuration to two pumps in series and we turn the second pump on, your flow will remain the same and your head will double, basically, will increase. So that is the difference in those configurations. And we want to remember this when we talk about parallel piping systems. So similarly, when we have two pipes in series and we're trying to determine the head loss across both pipes, the total head loss is the head loss through pipe segment A plus the head loss through pipe segment B. That's the total head loss for a given volumetric flow rate. Now, this is where things can get a bit more tricky. And so this is where we just want to take a moment to pause. And that is when we have a parallel piping system. So pipe A is parallel to pipe B, and pipe B is twice the pipe diameter of pipe A. When we start to flow and the water goes through pipe segment A, and it'll split to the other part to pipe segment B, the pressure drop from pipe A, like segment A through B, will equalize. So they'll be equal. And it's the same as the pressure drop from node 1, where the flow diverges, to nodal point 2, where the flow converges. But the volume from pipe segment A plus the volume of pipe segment B will be equal to the total volume flowing through in and out of that system. So that's the basic equations that we got to remember here. Now, if we wanted more flow through A, as we discussed last time, there's a few things we could do to pipe segment B. We could reduce the size of pipe segment B. We could put a balancing valve that would introduce what I like to term an artificial pressure drop across in pipe segment B, which would push more of the water into A. We could lengthen pipe segment B. That would also increase by increasing the length, the pressure drop per lineal foot would basically the pressure drop due to the pressure drop per lineal foot, because you're multiplying through by the length, would increase. And so all of those things, are, in terms of pipe segment B, that, modifications to pipe segment B would increase the flow through A and reduce the flow through B. Again, remembering our bottom volumetric equation. Now, the other thing we could do is increase the flow through A by increasing the pipe diameter of A, or we could introduce a pump into A. The only worry is if we introduce a pump to A is we would probably want some kind of check valve on pipe segment B to prevent the flow from just going in a clockwise circle there. So got to be mindful of some of the hydraulics there, but in general, modifications to B is what we're looking at. Now, most of our plumbing systems don't just have 2 parallel branches, they have more than that. And this is even fairly simple. When we're evaluating parallel piping systems, the first step we got to take is look at what the nodal points are. So in this case, I have here in the bottom, let me get my laser pointer out. In the bottom corner here, we have what a pump that is or a pump symbol that's representing our recirculation pump, our water heater source, and then there's a little line off the bottom of it that represents our cold water makeup. But this is a hot water recirculation system. So leaving the mechanical room, coming out, and let's assume it's to scale just for ease of concept, we get to a nodal point A1. The flow at that point, assuming a closed system for hot water return systems, which is typically our initial assumption, the flow diverges and you have it continuing on to the B and C loops and D loops, and then some of the piping going through A. And we're trying to figure out what the size is of our return lines. So the return line starts downstream of every plumbing fixture. In order to get the flow to not just flow into the A loop, we put on these balancing valves. If we didn't have the balancing valves in there, such as that I showed before, all the water would take the path of least resistance, which would be in this A loop. You would not see any circulation or recirculation of flow going out to this B, C, or D loops. But by putting in balancing valves in the A loop, the B loop, C loop, and D loop, as we discussed during our last meeting, this balancing valve will be the one that's likely the most closed, followed by this one, and the D loop would likely be the most open. But those balancing valves would create that artificial pressure drop across the valve that would push that water to the next path of least resistance all the way out through the rest of the system. And that's the purpose of the balancing valves that we have in this system. Now, let's talk about the equations governing this. First off, we need to kind of do a little bit of a process of elimination of which equations we shouldn't use. One of the errors that many young designers do is they will base all their flow off of velocity. This is the chart for copper tubing based on the Hayes and Williams equation, which we'll touch on later. But if you just go based off velocity, you'll notice that there's friction, pressure drop per 100 lineal feet on the bottom here, and then flow on the y-axis. You'll notice that the diameters are a positively sloped line and the velocities are a negatively sloped line. With those velocities being a negatively sloped line, you'll notice they cut across the pressure drops per 100 lineal feet. And often we're shooting or aiming for a uniform PSI per 100 lineal feet drop, recognizing that this might be a little bit of a challenge to obtain, but that's what our general design principles tend to be for simplification purposes. And as we're trying to hit that, the velocity will cut across that. So if we base our flow rates only on velocity and flow, you don't have control, because pumps are not sized based off velocity, they're sized off of pressure drop. Your pressure drop and your flow rate have to be adequate for your system to work. So we don't just use off velocity. So that's what this first X is. The other things we need to eliminate is some old design techniques, one of which is utilizing, as you can see here, I'm highlighting with this box, a 30 BTU per hour per lineal foot heat loss throughout the whole system. Do not use that. And I'll show you why, but in essence, you're going to end up with a system that's grossly oversized. Now, this chart on the right shows BTU losses based on a couple insulation thicknesses. And I have an X for this. This comes from ASPE's water heating design manual. This is actually good information. However, it's not expansive enough, because the assumed temperature for the system is 120 degrees Fahrenheit. Many of us as designers are starting to change our fluid temperatures, 140, 160, especially in regards to waterborne pathogens. So we can't use this one chart for all those instances. We need something that's a little bit more expanded. However, the information on this chart is good, and I would imagine that ASPE is in process of updating this. Again, the latest information is in the ASPE Legionella Design Guide, which would recommend getting yourselves a copy of if you already have not. So let's start with the base equations. And really the first one comes down to the conductivity of heat through our piping system and insulation. Now, I would refer you to your codes, both your energy codes, your plumbing codes. The energy code, the National Energy Code, International Energy Conservation Code, has a table in there that discusses flow rates based off, or excuse me, insulation thicknesses based off of fluid temperature and pipe size. So roughly for plumbing systems, it's a central bar. So 1 inch to 1.5 inches, and then 1.5 inches to 2 inches, based on a temperature of about 140 degrees Fahrenheit. Now, the question comes up, if you set your water heater at 140, should I use the 105 to 140 row, or should I use the 141 through 200 row? Take a look at your water heater manufacturer specific product information that gets installed, because most water heaters have a plus or minus 2%. So you could end up overshooting the 140 set temperature, in which case a code official may ding you and require you to go with the thicker insulation, or turn your water temperature down so you don't exceed that. So it has happened. It's one of those things to kind of be thoughtful of. The Uniform Plumbing Code has a different provision in there, which is to match the insulation wall thickness to the pipe diameter, which does have a more uniform BTU per hour per lineal foot loss. And we'll touch on that here in a little bit, but that's the two methods out there currently. Now, the base equation we're going to use, going back to our college days, is our thermal resistance equals our insulation thickness divided by thermal conductivity. And different materials have different thermal conductivity. Copper, for instance, has an incredibly high thermal conductivity, which means its resistance is low, because thermal conductivity and thermal resistance are inversely proportional. Insulation is the exact opposite. Insulation has a low thermal conductivity or a high thermal resistance. And so when you look at this example of an insulation manufacturer, you can see that based off of the chart here and the fluid temperature, you can make an assumption and probably interpolate a BTU, a thermal conductivity, probably in the range of, assuming 140 degrees Fahrenheit, probably around 0.25, 0.26, somewhere in that range. And you would plug that into that equation based off your insulation thickness. And again, we're going to assume copper is in essence negligible when we're going through this. And again, I'm using copper as a base material. If you're using other materials, it may be worth going through the calculation and adding that resistance to your overall, the resistance of the pipe material to the insulation thermal resistance. Now, when we plug in the next step of this, so our thermal resistance, so R equals LK, it could also be determined as conductance, so conductivity being one of the types of heat transfer. So conductivity times our surface area of our object times our temperature differential of the air, of basically the air to the outside air temperature from the outer layer of insulation to the inside fluid temperature, we make an assumption, and we have to make assumptions to kind of simplify this process a bit. There's going to be a delta T there. So assuming, let's say, our fluid temperature is 140 degrees, let's make the assumption that 140 degrees is what's on the inside of the insulation, that the copper wall is basically 140 degrees Fahrenheit. And so the inside wall of the insulation is 140 degrees. And then we're going to make the assumption that the outside wall is, let's say, 65 degrees Fahrenheit. Let's say it's a cold space, plenum space that the pipe is sitting in. So you have 65 degrees Fahrenheit as the second temperature. And that's going to calculate out what your heat transfer is. Now, we're talking about a pipe, right? Not a flat plate. So in essence, to convert that cylinder to a flat plate, we are going to change the equation slightly by, if in your mind, imagine that you slice down the side of the pipe, and then you're opening up the pipe to make it, single direction as opposed to radiating outwards. That's the modification in the equation here. So that's where you get your 2 pi, your 40.944 constants, and then your logarithmic derivative of a logarithmic root, of your outer diameter divided by your inner diameter. And again, keeping in mind that your inner insulation diameter is going to be smaller than your outer insulation diameter, just due to the fact that it's going around a pipe. So it's going to be a little bit of a trapezoid if you were to look at it from the side. Now, if you take those equations and you create charts, remember I told you that ASPE heating manual only had one of the conditions. If you start creating charts for 1 inch thick insulation, 1.5 inch thick insulation, 2 inch thick insulation for various pipe sizes and various fluid temperatures, you're going to create a chart where you can see different BTU losses per lineal foot for the different fluids and temperatures. And as you notice, as you increase pipe size, your fluid temperature, or your heat transfer rate increases. As you increase fluid temperature, your heat transfer rate increases. And again, we have some assumptions of a 0.24 BTU per hour, inch hour foot squared, basically for that insulation. And we're assuming a 65 degree Fahrenheit ambient air temperature. So again, some assumptions went into creating this, and this is kind of that next iteration that's in that ASPE Legionnaire design guide. Now, one thing I wanted to point out, I mentioned before about the Uniform Plumbing Code, for 100 degrees, 1 inch thick insulation, 1.5 inch thick insulation, and 2 inch thick insulation for the corresponding pipe size. Remember, I indicated that the heat transfer rate would be almost identical, and that's what we see here. So you end up with right around somewhere in the range of less than 4.5 BTU per hour per lineal foot when you match pipe size in those cases. And you would expect to see that as it continues to increase in size. So remembering our equations, again, these are the ones that we have so far. We have R equals LK. We have our thermal conductivity equals this equation down here. Then we add another equation, which is for our fluid flow. As that fluid flows through the pipe, we're going to see a temperature drop of the fluid. It's not going to stay uniform. We're going to make the assumption it stays uniform. But as that fluid flows through the piping system, it's going to dissipate heat to the space, and so that temperature is going to drop. Again, for simplification purposes, we're going to assume the same constant fluid flow temperature through the piping system. But in this case, it's not necessarily doing that. But so we have to recognize some of the limitations here. But that is the next equation. I think this one is one that most of us are familiar with, which is our volumetric flow rate times a 500 constant, assuming imperial US units, like gallons per minute and Fahrenheit, times our temperature differential of our fluid. So again, one is the conductivity through the insulation, the other one is the fluid temperature differential. So if we're going to create an image of this, right? So this is a cutaway of a pipe here with the water flowing through here from left to right. The T1, T2 that created those tables before for the various flow rates, we're describing this arrow that's going up, basically, or out from the pipe. The temperature drop of the fluid is this one we're describing from left to right. But that's one of the things we're trying to figure out, because we don't know what our volumetric flow rate is through our hot water recirculation system, again, for our supply and return. We're trying to figure that out. So that's one of our unknowns. And we also don't know what the temperature drop is through our fluid system, because we need, that's one of the things we're also trying to figure out. So we end up with this equation with two variables. So our next step we probably want to do is start looking at what our, trying to figure out another equation to maybe help us solve this one. So worth noting, though, just a quick note on velocity, is when we're looking at velocity, definitely take a look at pipe materials and recognize the pipe material limits, both on temperature and velocity and other things. When you look at copper, the Copper Development Association indicates that for systems where water temperatures are below 140 degrees Fahrenheit, we can use up to 5 feet per second in a hot water for a continuous flow. For systems that utilize a temperature over 140 degrees, like if you're thinking 150 or 160 because of waterborne pathogens, if that's one of your strategies, you have to lower your velocity to 2 to 3 feet per second. So, and also when you're calculating out your velocity, do not use nominal pipe size, use the inner diameter. Otherwise you're either more likely than not overestimating or potentially underestimating your capacity in your system. So this is where the Hazen-Williams equation comes in. So our head friction loss based off of a foot per 100 lineal feet times the constant 0.2083 times 100 divided by C, with C being that coefficient of friction that I mentioned here before. For copper, it's between 130 to 140 to the 1.852 power, in essence, squared, times our volumetric flow rate to the 1.852 power, again, in essence, our volumetric flow rates squared, divided by our internal pipe diameter to the 4.8655, in essence, to the 5th power. And between those, you will get a head friction loss. Now, some other equations, when you're calculating your head loss, you might want to look at volume and flush time, especially for systems that you're worried about from a flushing perspective. And this is something that we'll touch on maybe a little bit later, but these equations won't help you. But if you're already going to be solving for the other things, this might be a good opportunity to do that for. So when we come up with our list of equations, then we end up with what I would describe as these 4 equations. So the first one is our conductivity equation, right? Q equals, when we simplify it out, 2 pi times K times the delta T of 1 to 2 times this, or divided by 40.944, and that logarithmic root of outer diameter and the inner diameter of the insulation walls. Then we also have our heat transfer rate for our fluid flow and temperature. We also know that we have a velocity equation where we don't want to exceed a certain velocity, so we have to figure out our velocity, and that's based off of a volumetric flow times a constant divided by our area. And then last but not least, we have our head friction loss that equals what we just discussed. Basically, that is accounting for our volumetric or velocity losses through the internal diameter of the piping. Now, what I want you to pay attention to is these blue highlighted items in essence is one variable. It's all regarding around the area of the pipe. We then have our volumetric flow rate, which is a second variable. We have our temperature differential of our fluid, which is a third variable. We have our velocity, which is based off of the volumetric flow rate and the area, which is a fourth variable. And then we end up with a head friction loss, that is that fifth variable, and we have 4 equations. So we added equations, but we also added more variables, and there's no way to solve this by going this route. So what do? This is where we utilize a method that I first became aware of in that college course called the Howard-Cross methodology. It's also located in the Michael Lindbergh Mechanical Engineering Reference Manual. It's also located in the ASPE Legionella Design Guide as well as a point of how to use it. And this method basically utilizes a computer program, or you could even use Excel if you're going to do it a little bit manually. And in this method, flows in all of the branches are first assumed, and then adjustments are made in consecutive iterations to the assumed flow rate. So you have to go through and do multiple iterations for a hot water recirculation system, specifically the return, to figure out what the answer is and try to get your system honed in where you want it. And this was what I took a whole semester on. And it seems that ABET may have removed this as a requirement. So if we looked at a sample problem here, let's say assume a 140 degree Fahrenheit hot water system temperature, 400 lineal feet of 1-inch type L copper, and we'll assume that the energy code that changes with fluid temperature. If we wanted to find our flow rate, our temperature drop, our velocity, head loss of water, with our, in essence, 4 equations that we had, the 3 equations, 4 variables or 4 equations with 5 variables, depending on how you look at it. We could create a calculator, which we did as part of that ASPE Legionella Design Guide, and going through consecutive iterations using those equations. And here's just kind of the pointing out where those equations are. we could do, if we assumed a 1 GPM flow rate going through, we would end up with a 7.25 degree Fahrenheit temperature loss, a 0.41 foot per second maximum velocity, and 4.2 psi per 100 linear, or excuse me, 4.2 psi. And that was based off of the calculations. Now, if we bumped up that assumed flow rate, like Hardy Cross says, to 5 GPM, we would see the second go around as we answered these questions, the temperature drop would be 1.45 degrees Fahrenheit. So again, we increase flow rate, the temperature drop goes down. Our velocity increases for the second go around because our flow rate increases while we kept the pipe constant. And the head loss would increase because the velocity increases, and based on our Hazen-Williams equation, we would see that increase to 9.2 psi. Now, the one trick is when we're talking about doing the parallel pipe system sizing, we don't know what the size is for all the hot water return segments here. It's not known. This is one of the things we're trying to figure out because it's based off the flow. So a good approach in this case would be to take an initial guess, right? So when you do that initial iteration of assuming the flow, if we wanted to assume 1 GPM in each of these loops, I think could be pretty confident that each of the individual loops that only saw 1 GPM could be a ½ GPM, likely in this case, we probably would, or excuse me, a ½ pipe for that GPM. And then at this segment where we had 2 GPM, still could say a ½ And then as we increase to 3 GPM, we may want to increase to 3/4 inch, and 4 GPM would be still a 3/4 inch. So we'd see this progression that would look something like this, where it's a ½ inch, and then increasing to 3/4 inch as we go through. So you have to start off, but keep in mind when you make that assumption for the pipe size, that first go around, that when you make that assumption, that it's your first guess at that hot water return pipe size. So if you find that you have too large of a temperature drop through your system and you have to, let's say, increase the flow rate starting from 1 GPM, let's say you have to start bumping up the flow rate at some of the loops based on the balancing valve, you may need to increase your hot water return pipe size some, so that way you're not causing erosion corrosion depending on your pipe material. So if you do that though, remember our equations for heat loss, you're going to have an additional heat loss on your hot water return side. Now, some people will ask the question, well, Christoph, do I have to account for the hot water return temperature loss? Or aren't we only worried about supply? And what we make the argument on in the Ask Me the General Design Guide is that yes, you should, because you need to know what the temperature is coming back to your water heater. Further, with the advent of a lot of heat pump water heaters, the return temperature is an important part in how that system operates. You may actually want to see a larger temperature differential through your system. So yes, you will need to know your hot water return temperature and try to do your best to try to capture what that is based off the calculations. Now, we'll have some time for questions here at the end, but that's kind of the end of the theoretical side. So let's talk practical or practice. So theory and practice is what makes up expertise. So first off, when you're selecting your recirculation pump, right? When we went back through, let me go back a few slides here, and we got this result, the second iteration. Let's say we like the second iteration more. When we select the pump, we are not selecting the pump for 5 GPM and 2 feet per second, or 2.5 feet per second of velocity. We're selecting the pump based off of 5 GPM and a 9.2 psi pressure drop, because the pump will need to overcome that in order to recirculate through the system. So it's important when selecting a pump that we look at the pump curves and make sure that our point in our system is below the curve. I cannot tell you how many times I did quality control on projects and the plumbing designer would have, let's say they wanted to, they selected this pump, but their system was out here. That's never going to work. What's going to happen is the pump is going to operate at this range, or excuse me, it's going to go probably back to this range, and it's going to try to shoot for almost no flow and almost deadheading, more likely than not. Or you're going to burn it out because it keeps trying to hunt for that furthest point. So you need to make sure your point is inside the curve. Now, what a popular collection of pumps recently is variable speed recirculating pumps. The ASPE General Design Guide came up with recommendations to not put them on VFD control, but to have them as a constant flow and head, because the temperature in the system shouldn't be modulating all that much, and your flow and head shouldn't be modulating that much, other than when the system changes from closed to open. It should be, if you're sizing it correctly, the thinking went that you should be in a pretty fine-tuned area. However, the use of variable speed frequency, these ECM type motors for recirculating pumps was recommended, especially for healthcare facilities. And the reason for this is, rather than having to swap out a whole pump, you could select a point. Let's say this is our curve here. If you selected a point down here, you had a lot of wiggle room to increase head or increase flow as needed for your system. And that was the real beauty of these pumps. So we saw it as an opportunity to fine tune your system and give the owner more control. So that was one of the recommendations that came out from that document for consideration. Now, there's a lot of discussion about utilizing these with thermostatic balancing valves. And when that comes up, I think there's been a lot of cases. And that one, I think, as far as the ASPE General Design Group indicated, that was one that there's been a lot of reports of success in the field. And I think that that's definitely a topic that, getting a white paper written on that explains that process, I think will be really helpful for industry as well. So that's one that I think was left as a potential solution as well, if I recall correctly. Now, an important part as well of the hot water recirculation system strategies from a practice standpoint is making sure that the system is tested, balanced, and commissioned. Now, we're going to touch a little bit about balancing valves in a little bit, but one of the things that I think we're going to see an advent of, especially IATMO, we're involved with a lot of standards creation. We're going to see, I think, some product testing here in the near future for automatic balancing valves, so thermostatic, pressure independent, specifically for domestic hot water applications, and then electronic types. And those are going to be a different type of process of testing, balancing, and commissioning than a manual balancing valve, something which you have a CV on the side and you're trying to adjust, like the circuit setter type that, using the Kleenex brand type of name. That's a manual balancing valve. Those require a test and balancer, whereas the automatic balancing valves really is only commissioning. And so that's very important in order to get these systems working properly, as I demonstrated in my story early up front. But there's going to probably be a few more things that we need to do as plumbing design professionals. One of those include having a table showing the capacity of our hot water recirculation system. That includes the piping and the recirculation pump. We also should probably include some kind of chart in terms of with the capacity charts for these things on our plumbing plans, because if the owner needs to go back and modify a hot water recirculation system for a hospital, let's say they're adding 3 new loops, those loops should be checked to make sure against the overall system, to make sure that the existing system has capacity, both the pump and the pipes, that you're not exceeding velocity limits in the piping system, and that your pump has the capacity to take on the additional load, much like what we do when we size our incoming water mains, and also much like we do when we're doing electrical load analyses. Our hot water routing also has an impact. Keep in mind, our pressure drop is based off of a velocity and a given pressure drop per 100 lineal feet of pipe. So if you're using jump routing and going up and down fixtures, kind of like a purified water system, which is certainly one approach and one that was mentioned in that design guide as an option, that's going to increase your length. So you're going to have a greater pressure drop. You're probably going to need a little bit of a bigger recirculation pump to overcome that friction. On the flip side, if you're using with an elevated delivery temperature and you're going to use your point of use TMVs to reduce the temperature, and you're going to try to elevate your temperature, that's another approach. However, now you have an elevated temperature, and now you have to recognize if you're going over that 140, you may need to slow down your velocity a little bit. You may want to, just to prevent corrosion, especially on copper piping systems. Or for some plastic piping out there, once you exceed 140, the plastic derates. So you may have to, and some of them don't even allow usage over 140. So all these things we have to be thinking about at the same time as we're going through and doing design of hot water recirculation systems. I actually wrote an article about this and some of the trends in hot water control from a manufacturing, engineering design, and construction inspection standpoint. There's a QR code that the article was published in Plumbing Engineer magazine. That same QR code, I did touch on one of the things in terms of shutting on or off the pump. And this was something that was addressed in the 2024 Uniform Plumbing Code, and I'll touch on that code update. But one of the concerns, especially in healthcare and hospitality, where you have the highest incident rate of waterborne pathogen outbreaks and a number of litigations surrounding that, is when you add an aquastat to the pump and you turn off the pump when you meet the temperature, there is a potential in your most hydraulically remote loops that you end up in a situation where you never get out of Legionella growth temperature. So here's kind of an example of, there's a low temperature set point, so the pump turns on, and we have a system where the water is getting heated again by that symbol in the mechanical room and starts flowing out, and your A and or B loops are satisfied and they jump to temperature very quickly. And especially if this is an unbalanced system, but even in a balanced system, if you have enough loops that are close, you'll get to you potentially could get to your system set temperature. You get that water back to the water heater, and the aquastat turns off, and now your system starts to cool down before the pump re-engages. But what you'll notice is the C loop never quite gets to a hot temperature. That red piping never gets that hot temperature, which could mean that you have waterborne pathogen growth in that C loop because it's in essence not balanced or not designed in such a way that will ever get flow. This was actually part of the discussion in the 2024 Uniform Plumbing Code because enough engineers were having a problem with the International Energy Conservation Code in shutting off the pump with aquastats and trying to supersede sometimes and having arguments with the AHJ about which one should get installed. And so there's a new allowance in the Uniform Plumbing Code that says for healthcare facilities, long-term care facilities, hotels or motels, devices that automatically turn off their circulation pump or pumps shall not be required. So this is at least for UPC adopting jurisdictions, which is about half the country, a little less than half. This is an opportunity to have something to point to say, hey, we don't want to turn off the aquastat, or we don't want to turn off the recirculation pump because of the health and safety concern. Some other things that are coming up on the practical side is digital mixing valves. There was an article, there's a QR code that was put into Working Pressure magazine, which is the magazine of ASSE International. Would recommend getting a free subscription to that. It's a really great publication, lots of good articles in there. And this article put out the need for a new product standard that kind of goes above and beyond what ASSE 1017 does, which is for master mixing valves. This led to the formation of IATMO IGC 384, which is in process of hopefully becoming ASSE 1118 and ANSI standard for digital mixing valves for recirculating hot water systems. And there's the QR code. I'm happy to report that all IATMO IGCs are for free viewing, and actually all IATMO and ASSE codes and standards have a free online viewer on our webpage, and so that one should take you to that webpage. As I mentioned before, we also have these classifications, manual balancing valves where you have to adjust this dial to hit a CV value, which is governed by this equation, which is why you have a test and balancer occurring. That is, a different approach to balancing as opposed to automatic balancing valves, which include pressure independent balancing valves, both fixed cartridge and adjustable type, thermostatic balancing valves, which include fixed cartridge and adjustable types, and then electronically actuated balancing valves. And another new standard, one that you may want to include in your specs, just like IGC 384, is IGC 368, which will hopefully eventually become ASSE 1115, which will be there for thermostatic balancing valves. And the thermostatic balancing valves, IGC, the goal is to create an automatic balancing valve standard around that. So these are good ones to look at as potential opportunities in specs improvement. I'd be remiss if I didn't talk about right sizing. As we mentioned before, the larger the pipe, the more heat dissipation. And so if you reduce your supply pipe size, like using the water demand calculator, which would be approved for multifamily buildings, let's say, and we're working on the commercial sizing for healthcare, hospitality, offices, schools, and the like. By reducing your supply size, you're gonna not need as much flow through your return side. So it's definitely worthwhile right sizing your system. And there's the QR code if you wanna get to the IATMO water demand calculator webpage. So as I'm kind of wrapping things up here, one of the things I hope that you're recognizing is that we're kind of going in the plumbing design professionals and plumbing engineering as a whole, it's kind of going through a change engineering at this time. So I would make the argument from my observation and just from my years of experience, when we started talking about complexity of systems, early in my career, plumbing systems were relatively relatively simple in terms of the design principles, and HVAC, at least from how it was explained to me, was relatively complex. I don't know what the time frame is, but it seems right now to me, if I'm going to make a prediction, that in a number of years, plumbing engineering is going to become more complex than HVAC engineering. And the reason I say that is because we're starting to delve in this whole realm of water quality, including waterborne pathogens and other contaminants in water. And we're recognizing that some of the assumptions we had in terms of how we engineered our plumbing systems, including hot water recirculation systems, may not have been the best. And so we're really coming close to this nexus point. I don't know when that's going to occur. If I would make an estimate, I think in the next 3 to 5 years. But there's going to come an inflection point where plumbing engineering is going to become much more complex than HVAC engineering. And that even came from a conversation I had with the former director of engineering for a company that was asking me, hey, for duct sizing, we just want to use a uniform duct size because it's easier for the installer to put this in, and it makes our calculation simpler. So there's kind of a rule of thumb there. The director of engineering asked me, can we go ahead and do the same thing for the plumbing size? And I said, actually, if anything, we're going to be going the opposite direction on the plumbing side because water age is such a big concern. So I think we're going to get that nexus point there very, very soon. And really, when you look at what's happening in industry, like ASPE's Professional Engineering Working Group, getting closer and closer to creating a plumbing exam under the mechanical discipline, I think this shows. I think when you look at IATMO and ASSE, which sent a letter of support to ASPE as part of this effort, when you look at even organizations like IATMO and ASSE, we now have additional certifications for various plumbing components, both for the installers, the designers, the inspectors, and others. So we're starting to understand that education and knowing more about plumbing systems is going to be an important part to making sure these systems are designed, installed, commissioned, and maintained correctly. If you want to stay in the know, I would recommend subscribing to the IATMO Standards newsletter. This is one of my favorites, and I'm not just saying that as an IATMO employee. Honestly, it's amazing to see all the new standards that are coming out. There's opportunities to comment on there. Just to stay in the know, I would say definitely subscribe to that. It's really a worthwhile information, and you can kind of get a sense of how the industry is moving forward. Also, if you're interested, IATMO, we have 2 innovative task groups that are currently ongoing that will impact this work directly. The first has been ongoing for the last number of years, the Water Demand Calculator Task Group. We're looking at commercial buildings. The other is one that we're going to initiate here in Q2 of this year, which is a hot water recirculation design, installation, commissioning, and maintenance task group. And we still have an open call for task group members through the end of this month. So if you're interested, would love to have you sign up. The meetings will be, I think for the most part, will be all virtual. There won't be a requirement to show up in person, although we may have an in-person meeting. We'll have to see if we can get the group together. But the goal will be help kind of working through some of these processes and improving things, and hopefully also eventually ending up to an ANSI standard. So if you want to get engaged and you want to help out with this, that's a great opportunity. Finally, hopefully what you notice is that groups like ASPE, like IATMO, ASSE International, folks like Caleffi that manufacture these products, engineering firms that focus and have plumbing engineering professionals, there's a need for that. And really that expertise comes from deep specialization. Peter Drucker, who is one of the best authors on management and knowledge work back in 1974, Cal Newport would also kind of refers to him if you've ever read his books, Deep Work. And he talks about how knowledge, because it rapidly deteriorates unless it is used constantly, maintaining within an organization, and I would argue within an individual, an activity that is used only intermittently guarantees incompetence. And so we really want to be careful because obviously, as you can tell here, there's a lot to know. And so we don't want to stretch ourselves too thin. And really specialization is and that understanding of theory and practice is the real value proposition for our clients in the end run. So again, kind of a key takeaways and discussion, the Hardy Cross method, I think is going to become more used by plumbing design professionals over the next decade. I think we're going to see a lot of codes and standards innovation around hot water systems. And really, I would argue that IATMO is already at the forefront of this, along with ASPE and other organizations. And I think to get involved, look at IATMO's innovation task groups or the uniform codes process, because really, if you want to change industry or if you want to have an impact on a larger scale than just on a project by project basis, that's the way to get it done. It's going to be in codes and standards work. So if you have any questions or want to talk to me further, there's my email address. I also have a newsletter that I publish on LinkedIn called Plumbing Science. That's a QR code if you want to go ahead and subscribe. Would love to stay in touch. You're more than welcome to connect with me on LinkedIn as well, or by email. And with that, I'll turn it back over to you, Kevin.
Wow, that was great. Thank you, Christoph. We do have time for questions, and we just have a couple more slides, and then we're going to answer some of those questions. So if you typed in a question, or I have some helpers behind the scenes here, we'll take some of those questions in just a minute. That was great, Christoph. I feel like I'm back in college a little bit. I love the, by the way, the QR codes. Everybody remember, this will be on YouTube, so you can go later if you didn't get all these QR codes and take a picture of those later. I love the IGC standards. That's great. I didn't know about those, and we will devour those for sure. And go ahead and let's go through a couple of more slides, and then we'll get to our questions. So at Caleffi here, we have a great technical support team. We have a phone line there that comes directly to the team, and we have an email. We invite your inquiries, your questions about the application, about the theories that Christoph talked about, or about our products. So we're there for you. We do have a podcast that's really popular with Greg and Dan. That's available on the caleffi.com website as well. So if you have 15 or 20 minutes and you want to listen to some good discussion on the industry, tune us in. And of course, we love your social media posts. We like your pictures, your stories. We like to learn about your companies, what you're doing. And if you have pictures of Caleffi products, that's even better. So we are on all of these media. All right, so I had a couple quick questions. Then I'm going to ask my colleagues, Bob and Cody and Greg and the other guys. But you mentioned that white paper on thermostatic mixing valves. Excuse me, on thermostatic mixing valves and smart pumps. Is that an existing white paper?
It's not an existing white paper. I think it's one that there's been a lot of discussion about, a need, I think, for industry to put one on. So I think that's a topic that's definitely of interest for me. I would love to find some collaborators on to kind of develop that. At ATMO, we do develop several white papers on topics. I think there's a lot of individual data points, right, of that working. And so trying to understand the mechanics of it is one that's out there. And I've heard several folks that have an interest in that. So it was more of a mention of, hey, if that's a topic you're interested in doing some writing on and development on, would love to have a conversation and see what we can develop in that regard.
Great. Okay, let's look for some questions. We have 6 or 7 minutes here. Bob Rohr, did you see any questions out there that you'd like to bring up from the attendees?
Well, oddly, quite a few of the questions were answered on the next slide after the person posted the question, but there are a couple here that I think I could throw out there. They said you referred to the IECC version 2015, is it? They asked many changes on the newest version of it. Is it 21 or 24? What's the newest version of that code?
So I think the 2024 code right now is still being released. I think there was, I think a lot of debate that was going on around that one. So I think that one has yet to be released. So it's kind of a little bit been hung up a little bit. The latest version out there is 2021, and to my knowledge, those charts have not changed significantly, at least impacting the insulation thickness. So that's at least on my latest review of those. I know I used the 2015 in there, but I think that the 2018 and 2021 were the same in essence.
All right, thanks. And then a question about the UPC calculator. I guess a commercial version of that, I think you said through the presentation, is in the works, because that I know comes up a lot to us also, that, what if I have flush valves, et cetera, et cetera. So I think that that's an ongoing project. So
yeah, and really my team and I were working on that together with, I think at this point we have about 30 to 40 volunteers and collaborators, and really we're making huge inroads this year. So I'm really excited about the near future of having something available from a commercial standpoint. So definitely stay tuned. You can actually subscribe to the IATMO. If you just Google IATMO water demand calculator, there is a link in there that you can subscribe to the latest updates. And again, if you want to stay in touch with myself and anybody else from IATMO, it's a great way to kind of see what the latest and greatest is. But yeah, definitely stay tuned. It's in the works. We're making great strides.
All right, thanks for that. And then a couple questions were, yes, this presentation will be available on the Caleffi YouTube channel. It probably takes a week sometimes before we get it crunched and put up there, but I think 2 or 3 people ask about that. But yeah, I think the other ones, I mean, there's not a lot of them, so maybe, Christoph, you can respond to these people directly. Some of them refer to the slide you're on and the formula you're using, which, again, without slide numbers, I couldn't really go back to where they were when they asked the question. So anybody else out there see anything that jumps out? There's still a couple coming in, so I'm trying to scroll through them here, see if there's something. Oh, your email, which I guess you just put up there. I don't know if you want to put that up again. Somebody's asking about the contact information. Yeah, anything else that you saw, Kevin or Greg or anybody else?
Hey guys, it's Cody. There was a question in here that I thought was just interesting. Somebody had asked about when you're sizing for heat loss and everything like that, do you calculate the heat loss for the supply only or for both supply and return? And I'm pretty sure that's application specific more than anything, but what are your thoughts, Christoph?
Yeah, so in the ASPE Legionella task group that created that design guide, that again can be you can get through the ASPE bookstore site. We recommended actually determining the temperature drop through the supply and the return. One of the things that we recognize, especially from a waterborne pathogen standpoint, is if your return piping ends up getting in that temperature range, that can become a breeding ground. So you really want to know what your return piping temperature is from that standpoint. Now, for not all buildings fall under ASHRAE 188, right? We're typically talking, if you look at the 6 criteria, and even 514 now that's been released, we're typically talking about healthcare, hospitality, multifamily with a centralized water heater. So if you have decentralized water heating, then not so much. You're talking about buildings with complex hot water systems in essence. So if you have a simple office, or let's say a grocery store, at this time schools don't necessarily fall underneath it. Although I would imagine we're going to start seeing, especially with a lot more kids having immunocompromised systems, because diabetes and other things are considered immunocompromised. I think we're going to, not every building type is going to fall underneath that. That said, if you're using heat pump water heaters, you want to know what that return temperature is because it impacts the efficiency of your heat pump water heater. So really, I think even outside of the waterborne pathogen concern and just in general, it's going to be good practice to get in the habit of determining what your hot water return temperature is so you have better control over your system. And you really want to fine tune it anyway to really understand what's going on throughout. So I think the general recommendation, and I think the way the industry is going, is you want to know supply and return, even though your fixture only sees supply.
For sure, great commentary there, Christoph. Thank you.
There's the equations I think that people were probably asking about. So I can put up my contact information a little bit later. But again, it's four equations. This first one up here, and then the next 3, and then you have five variables. And so that's where you have to make that assumption about flow to start with V, and then once you make that assumption, you can start solving for each one of the other equations.
Okay, any more questions? Greg, did you see any, or Bob, any more that came in?
Yeah, like I said, I think you're answering them pretty much as we go along here, but when you get a chance, Christoph, page through them. There's something specific to you and to your methodology here. I think probably better to answer that offline, and for some product names and stuff like that, which we won't get into. I think we talked about that. So brand names anyways.
I had a question for you, Christoph. In terms of balancing and a balancing contractor creating a balancing report for the client, we know that if they're using manual balancing valves, they can use their differential pressure tool and generate a balancing report and write down all the pressure drops and the GPMs. Is it a problem with thermostatic balancing valves that you don't test them? I mean, you don't have the ability to hook a differential pressure tool up to those. You can't really tell. Can a balancing report still be created when thermostatic balancing valves are installed?
So that's a really great question, Kevin, and that definitely speaks to the practice side of things. So from my recollection, the ASPE Legionella Design Guide, what we agreed to as a group was we delineated testing and balancing and commissioning. So we said that your whole hot water recirculation system should always be commissioned. So in the sense, verify that the flows are flowing, that you're getting hot water in each of those loops. So a port could be useful to just knowing and verifying that you get flow upstream and downstream. But really, when you talk about automatic balancing valves, again, pressure independent type, thermostatic, or electronic, none of them have a requirement to be tested and balanced because they're automatically balancing. They're going to do it themselves. So you've eliminated that labor, in essence, that requirement, as opposed to a manual valve, which you have to dial in the CV. Now, as I mentioned in my last class, we talked about this a little bit more, but it's worth, I think, repeating here, is when you're doing manual adjustments and you're adjusting a manual balancing valve and you start going down the line and adjusting other balancing valves, you have to go back through, because you might get the flow rate right on that A loop, let's say, and then you get it right for the B loop. But the second you adjust on the B loop, you're impacting the A loop. You're gonna have to go back and forth between those two. Then you have to go to the C loop and you're gonna have to do it all over again. So if you have a system that has 50, 100 balancing valves, I mean, you're talking about probably days, if not weeks worth of effort trying to get that system balanced, as opposed to an automatically balanced system that's predominantly made up of automatic balancing valves, where the valves are doing that work for you. And that's really a lot of the guidance in that Ask Me the General Design Guide pointed to that difference. Like, yeah, the advantage of the manual balancing valves is that they're adjustable. The disadvantage is they're adjustable, and you have to adjust them in order to get them to work right. And that should be a consideration as part of the design. So it's not necessarily saying one valve over another type, but it's to be very mindful of that in your system. If you're going to work in like a healthcare facility with a lot of loops and a lot of changes, that could add a lot of cost to renovation projects, because you really have to go through and modify every single balancing valve in the system anytime you touch or modify the hot water return system. As opposed to an automatic balancing valve, as long as your piping has capacity and your pump has capacity, the system will figure itself out, in essence. And so that was the recommendation that we put together in that Ask Me the General Design Guide to demonstrate, the difference in approach. Now, if you need to adjust the flow rate in one of those branches and you have a cartridge type automatic balancing valve, you may be a little bit stuck. You might have to swap out the whole system. An adjustable, automatic balancing valve may be a good fit, but sometimes your control range for the automatic types, again, depends on manufacturer, may not be as good as for a cartridge type. So this is the really deep dive and understanding how this device, which is needed, impacts the whole system. So does that answer the question, Kevin?
Yeah. So really, for the client, the documentation to prove that the system was installed according to the design and is working properly might be more of a commissioning report that says the temperatures were checked. Yes, all the fixture piping is up to temperature, and the system is functioning as designed. Okay.
Yep. So I would say the testing and balancing is separate from the commissioning, and so all automatic, all balancing valves, automatic or manual, should be commissioned. You should make sure that the system works. Some third party probably should come in and double check it.
Yeah.
But when you have a manual valve, you need the testing and balancing, whereas the automatic, you don't.
Well, thank you very, very much, Christoph. It was a great webinar. We appreciate you. We hope to have you back again someday. And for all those questions that didn't get answered, we here at Caleffi will try and answer those in an email, or we'll send them over to Christoph and he'll respond. So again, thanks everybody for attending. It was a wonderful webinar. See you later, Christoph. Bye, everybody.
Kevin.